Now, next job is to specify the conjugate. Should have parenthesized that conjugate priors or priors for sigma square. And in many cases, you will see a lot of applications, say that they're going to use inverse gamma. And here I'm going to explain why they would choose inverse gamma. Why not choose, let's say, gamma or simply, exponential distribution? Of course, exponential distribution also applies, but let's talk about inverse gamma. So what is inverse gamma? Let's study this inverse gamma distribution. Okay, so when we say a random variable follows a inverse gamma distribution, so this random variable is x, then its probability density function follows this form. Pretty complicated, right? We have this term here is beta raised to power alpha. Okay, so what is beta? Beta has to be greater than 0. It is a parameter in this gamma function. So this is not a slope as discussed in previous slides. Okay, so this is a different thing, a different parameter. This is called scale parameter. So related to dispersion or variance, right? And what is alpha? Alpha is greater than 0, and it's called shape. For example, how peaked a distribution is. It is not location. Location only, relatively speaking, ballpark is parallelly shift a distribution. This is a different. So for gamma, inverse gamma distribution, it has 2 parameters, okay? And then multiply by x, this random variable, raised to the power of negative alpha plus minus 1, then multiply by the exponential function of negative beta over this random variable. Pretty complicated. I think I need to spend a couple of seconds to go over this gamma distribution. Also, a gamma function, also pretty complicated. So what is gamma function? When we say gamma n, if n is a positive integer, then gamma n is equal to n minus 1 factorial. What if what's in the function, the variable is not a positive integer? Let's say z, okay? Then gamma z is equal to this integral, okay? Integral, to integrate from 0 to positive infinity, okay? And then, okay, for x raised to the power of z minus 1 multiplied by the exponential of negative z, and integrate, okay, from 0 to positive infinity. Okay, remember that to simulate the posterior, any constant, when I say constant, or constants, or constant terms, we refer to terms that do not involve the parameters. They will be dropped because they don't affect our derivation of posterior. Okay, they only serve as proportionality function. So in this case, if we assume sigma square, okay, this variance term, okay, to follow a gamma distribution, we should feel safe to drop this term because this term does not involve the random variable. So this random variable here is x, right? And in our case, the random variable is sigma square. Okay, so for the first term is x raised to the power of, this random variable raised to the power of negative alpha minus 1. So this becomes what? Sigma square. And this becomes what? Sigma square. Everything else stays the same. The only thing that differs is this leading term is dropped because it's just constant proportionality term. Well, in the limit, if we let the parameters alpha and beta, so alpha and beta approach 0, okay? So let's say if beta equal to 0, then what is that equal to? Equal to 1, okay? And alpha also approach 0, then this term is gonna be what? Approach what? Sigma square, what? Negative what? 0 plus 1. Okay, and the second term becomes 1, right? Then we can have a non-informative prior as 1 over sigma squared. So in this case, usually we would set alpha to be a very small number, almost 0. Okay, and beta similarly. Okay. Then the posterior for sigma square given conditional on beta, okay, and xy is these. You can remember that we have this, product, right, to multiply through all probability density, right, across all cases, right? That's the reason why we have n here, n here. And so what does it look like? Well, again, it looks like a what? An inverse gamma distribution. And what about its, alpha? It turns out alpha equal to the sample size divided by 2, and beta is equal to this epsilon prime epsilon. So here, epsilon is equal to, actually, it is the error term, right? Equal to y minus x beta, right? Simplify. Okay. Right. So this is posterior, but conditional on beta. And in this case, if you recall, we can use Gibbs sampler to simulate posterior, right? MC, because Gibbs sampler is basically conditional, right? When we execute MC simulation for a single parameter, its posterior is conditioned on other parameters, basically fixed, right? So what's the next step? Toss these likelihood and prior into, this MC machinery, and it's going to crunch out posterior. And in this case, turns out to be conjugate priors. Okay.